Welcome to Everything Distributed. Today, we are going to talk about something that's slightly different from distributed computing, but that is very relevant to fundamental computer science. And then the technique we are going to talk about is called reduction, and particularly we focus on its application to distributed problems and distributed systems. So what is a reduction? If you have taken algorithms, you should know about this. And here's a recap on the definition. When we say a problem X reduces to problem Y, meaning that if we can use an algorithm for Y to devise an algorithm for X, okay? So in this example, I always try to draw something because that I could never remember the direction for reduction. And if you read the definition, you can say that, what do we mean by use an algorithm Y? So Y is kind of like a black box, like an API or like a library that you can use. So this is the algorithm for Y, okay? Algorithm for Y. And then you use this thing to design something for the problem X. So the outer larger rectangle is called algorithm for X, okay? And then the key for reduction is that you are going to use this smaller rectangle as a black box. And then the circle, the meaning of circle will become clear later. So now that's a reduction. Then here is a very simple but like concrete example. Suppose I want to find the minimum value of an unsorted array. And there are many different ways of solving this, but like let's assume that one of the simplest, it might not be most efficient, but like it will tell you the beauty for reduction. So at first, what kind of input do we have? The input is like some of the unsorted array. Uh, let's say, okay, here you have an unsorted array. Okay, then what do you do is that usually in the process of doing reduction, we need to do some pre-processing of your input data to transform it so that it can be used as an input for the black box here. But here for the black box, actually, we are going to use sorting so that we don't actually need to do anything. Then we can directly pass the same array data here into the black box. And then the black box will output, what's the output for this black box? The sorting algorithm, it will output the sorted array. Okay, then what do you do for the output for the algorithm for X, meaning that I want to find a minimum. So what you do is that, okay, here I'm going to pick the minimum here in this the blue circle, and then this, the thing that you output for the big thing is called a minimum. Okay, you might say that, okay, in this example, why do we want to use this thing? It's not very efficient, and then that's true. But like if you write the code, it's actually simple because that you utilize some of the power of a black box. And then this is very useful in many of the more complicated problems. And why do we care about this kind of reduction? And then the reason is that there are two main directions. The first one is positive direction, is that if I already know the solution for y, then I know how to solve x. So for example, suppose that you forget that how to use a for loop to find a minimum value, but you say that, hey, there's an API that can do the sorting. So you know how to do sorting because someone already implemented for you and you can solve this problem. Exactly use this kind of reduction. And then I think that's pretty obvious. Most of you already know this. But what a confusing thing is the other direction. It's on the negative implementation. It's that if there's no solution for x, what it means is that I don't have this algorithm x. Oops. Here, I don't have this. Then I know that I cannot have algorithm y. Okay, so that's the negative direction. And try to think about it, and then we will use an example to illustrate what the meaning is. Okay. Then yeah, there are also other kind of fancier usage, especially in theoretical computer science, is that the complexity, like computational complexity, message complexity, and bit complexity, like we all usually use that reduction to prove something, but that is beyond the scope. Okay, now let's get back to the negative direction. Yeah, so positive one, we already explained this. There's skip this, but like for the negative one, right? So let me repeat again. What does a problem X reduces to problem Y mean? The first thing is that the outer box is the solution for problem X. The inner box is the solution for Y, problem Y. Okay. So the negative implementation is that if there's no solution for X, nothing for the outer box because someone already proved something, then what can you say? You say if I come up with a reduction, then I know there's no solution for the inner rectangle. There's no solution for what? So now let's look at a concrete example. Let's say that let me move this. So this outer box is X, and then the inner box is Y. Okay. Then suppose we already know that it is impossible to travel beyond the speed of light because of a limitation of physics. So what you know is that in terms of this figure is that it's impossible to have this outer box. Okay, so this is not possible. But suppose that someone tell you that, hey, you know what? Just like let me build this machine A for you. So this is the machine A. Then what you need to do is that you enter this machine, and then this machine will travel faster than light. Okay. So effectively, this is a reduction. You use this machine, even though you don't know what's inside, how it is built. You say, hey, this can travel beyond the light, faster than light. So what's the implication? Because we already know this, we cannot travel beyond the speed of light. So what's a reasonable implication is that this guy is lying to you. You don't have this kind of machine at all. So this is the negative direction. If you know that there's no solution for the outer box, then you know that there's no solution for the inner box. Okay, so that's the beauty of reduction. And then negative, this implementation is a very useful proof techniques. Okay. Then let's look at the more relevant, the problems that's more relevant to distributed system. So last time we talked about this idea for leader election. Intuitively is that you have several nodes that try to become the leader. For example, we can use it for consensus, we can use it for leader-based replication, and many useful things. And intuitively, what it tries to do is that you want to select a leader so that every other knows if they have not failed yet, they will know the identity for the leader. And then the key thing I want you to do is that to show that it's actually impossible to achieve or to solve leader election in the asynchronous system and if you have a cross failure. Okay. And again, we are going to use this reduction. We are going to use something small to build something larger. And then something directly come to mind is that, hey, we have asynchrony, we have crush. So the first thing you should think about is FLP. It is impossible to solve consensus under this model. Then the next question is that, should I use leader election to solve consensus, or should I use consensus to solve leader election? And so that we can actually prove that leader election is impossible. Let's start with one side. use consensus for solve leader election. So what that is that the outer box, the problem we try to solve is leader election, and we are going to use some consensus as a black box. So how do we do this? Is that first each one has its own ID, and then you just use this ID as the input of consensus. So is that consensus? What's consensus? Someone might fail, someone might some message might be delayed, but eventually you have some output for consensus. And then because some output, what's the output? Output is some ID of the nodes. So you just use this output as the ID of the leader, then everyone knows that who the leader is, and then this is the leader election. So now that's good. We have a reduction. But what does the implication? What is the implication? And then and where can we apply FLP? So what's the meaning for FLP is that you cannot have where is this? Sorry. Oops. I should go to the previous slide here. The implication of FLP is that you don't have the inner black box. You cannot solve consensus in this case. But what that means is that you cannot use consensus to solve leader election. So this reduction is actually wrong. It cannot be implemented. But it has nothing to do with leader election itself. The thing you want to prove that's infeasible, right? One reason is that you only show that it's impossible to use consensus in this particular way. Then maybe there's other way to use consensus, and maybe there's another thing that you don't need to use consensus, so and you can still solve leader election, right? So if you use this direction, use consensus for solving LE, then it's inconclusive. It does not lead to the conclusion that you want to prove. Okay. So what we need is actually the other direction. We want to use leader election for solving consensus. So what does that mean? The outer box is consensus, and then the inner box is leader election. Okay. So what's a consensus? Consensus is that you have some input value, and then here you just use that as your ID. Then leader election will generate some of the ID, or that you can use that thing to piggyback when in your leader election protocol. And then the leader election will generate some leader's ID. Then what you want to do to solve the consensus is that you are going to output the input for this leader's ID. Okay, so that would be your input. That would be your output, and this solve consensus. And so what's the implication? Now the implication is that FLP, we know that this consensus is impossible to solve. So it's actually that impossible to solve leader election in this particular case. So why is that? If you remember from our previous example, this C, the outer thing, is like traveling faster than light. And what's inside thing? The thing inside is that the machine A, some magical machine that can travel faster than light. Then you know that because outer thing is impossible, so the inner thing is actually impossible. Okay, so that's the beauty of using the negative implication for reduction. And then there are many applications of using reduction to figure out like whether something is possible or impossible to solve in distributed system, and what kind of failure is possible, what kind of guarantee is possible, and whether I need to do some relaxation or not. For example, blockchain and consensus, total ordering message delivery and consensus, and other kind of shared memory primitive, and some of the concurrent data structure. Then yeah, basically we use all kind of reduction to show that something is possible or something is impossible. Okay, that's all I want to talk about today, and it's the idea of doing reduction. And if you are into computer science, if you know something about computational thinking, you will want to master this skill. because it tells you that something is possible or something is not possible. And then that's the two implication I want you to remember. The positive reduction, you can use solution for X to solve problem Y. And the negative direction is that if you something is not possible for the outer box, then you know that the thing is not possible for the inner box. Okay, that's all. Thank you.